Boom. All right, there we go. Man, it's been so long since I fooled with this stuff. All right, so I think I'm good now. I think we can do this. All right, so today what we're going to do some buffer overflows. And specifically, we're going to focus on VULNSERVER. So what is VULNSERVER? So basically, it's just a vulnerable application that you can use to practice your exploiting skills. So if you want to download it, you can just hop on over to this website, download it, and you can follow along. All right, so I already have it downloaded here. And let's go ahead and fire it up. So basically it's just a socket-based application. So we can connect to it. Let's see, where is my shell? So if we use Netcat, let's see if it's still open. All right, there we go. So if we type help, we can see that this application has a bunch of different commands. The commands don't really do anything. They're just there for you to exploit. So let's just take a look at one real quick. The first one we're going to focus on is this TRUN. And you can see all it does is just says complete. But I happen to know for a fact that this specific command is vulnerable. So we're going to focus on that. And later on, I'm going to make a nice polished video walkthrough on how to do this. But I just wanted to get something out tonight because I was bored and I haven't done any videos in a while. So let's hack some shit. All right. So the first thing we want to do is we want to fuzz this application. So, what is fuzzing? Fuzzing is basically the process of just throwing a bunch of shit at a program and trying to make it break. So you could send, different types of data it's not expecting, basically just anything that you can throw at it to try to make it crash. So what we're going to be using is a Python framework called BooFuzz, and you can just install that with pip. Just like that. Oh, yeah, that's right. It's installing it for Python 2. Okay, sorry, I got distracted. So you see it's going to install a bunch of shit. Just go ahead and let it do its thing. All right, so let's just go ahead and write our fuzzer. So basically BooFuzz is a platform to fuzz another application. So it does a lot of the heavy lifting for you. You don't have to write all the code that's going to create all the random data to throw at the application. But in order for BooFuzz to work, you still have to write some code in order for it to understand what it needs to generate and throw at the application. So let's go ahead and just get started writing our fuzzing script. So first off, let me get this going on over here. So we want to import everything from BooFuzz. All right. So we're going to get our imports for BooFuzz. Now what we want to do is we want to create a session, because remember we're going to create basically a TCP socket to that vulnerable server and throw a bunch of crap at it. So we're going to create a variable called session, and in BooFuzz we're going to call the basically session class, and then we're going to set our target. Also going to instantiate a target object. Now we're going to declare a variable called connection. This is going to be a socket connection. So we're going to instantiate the socket connection class from BooFuzz. And now we're going to put in the IP address of our remote application. And that's the server that's running VULNSERVER. So I think I have this address correct. After we do that, we need to input the port that it's running on, and by default, VULNSERVER runs on port 9999. And let's just go ahead and verify that this application is actually running on port 999. And you can do that by running the netstat command. So just do netstat, not any, let's kill that, and do ant, and bring that back over here. I just totally lost that. Actually, let me stop that. So we're going to do that. And then find stir. And you can see there are multiple connections open on 999. So we're good to go. We can see that it's actually running. All right, let's get back to here. So let's go ahead and finish out this line. And the last thing we need to do is specify the protocol that we're going to use to connect to the application, and we're going to use TCP. All right, we're going to close that off. Now, I know that probably looks like, you know, a lot right there, but basically what we're doing is we're creating a socket connection, and we're going to connect to the server on 999 using TCP, and we're just storing that in the connection variable. And we're also specifying that as the target and storing that in the target variable. And then finally, we're bringing all that together to create our session and storing that in the session variable. All right, pretty simple. Let's see, if you guys have any questions as we start diving into stuff, feel free. All right, so now that we have basically the code that is going to create the connection to the server, now we can start working on basically defining how BooFuzz will throw random data at our application. So what we need to do is basically initialize, and this is just telling BooFuzz that, hey, we're starting something. And then you want to give it a name. It doesn't matter what the name is, just give it a name. And I'm going to give it the name of the command that we're going to fuzz. Now we're going to use this static function. And this just means that BooFuzz, whatever is in this function right here, this text, BooFuzz is not going to touch it. It's not going to do anything to it. It's just going to leave it exactly as is. All right, so now what we want to do is we want to specify our delimiter. And as you saw earlier, when I typed in the command, you type the command space and then some text. So we need to tell BooFuzz, you know, we need a space after that static text. All right, and we're almost done here. And then finally, this is where we're going to have BooFuzz throw a bunch of crap at the wall. So I'm just going to enter some random text here. I'm just entering in a bunch of A's. You can put in whatever you want. Doesn't really matter. But this is just telling BooFuzz like, hey, randomize this. Throw a bunch of crap in this variable. All right. And now all we need to do is now tell boofuzz, go ahead and connect. And remember, we created that session variable, which created our session object. And we're going to use the sget function to specify what we're going to fuzz. And that is basically what this text is right here. Because we could create multiple, I forget what you call these exactly, but we could create, you know, a fuzzer for the TRUN command. We could create a fuzzer for the srun command, and we can have them all run sequentially. So that's why you need to specify right here which specific fuzz session you're working with. All right. And the last thing we need to do is just simply tell boofuzz to fuzz. And this is where it will actually reach out to the server and start sending it a bunch of data. All right, so let me check out something here. All right, looking good. Okay, so let's go ahead and close this, and we will save it. So now before we actually run our fuzzer, what we want to do now is run our debugger. And I'm using Immunity Debugger. You can just go to Google and just search for Immunity Debugger, and you can download the free version, which is the version I'm using right here. All right, so once this is open, you want to go to File and Attach. And you want to find the VULNSERVER process and then attach to it. So that's basically going to get your debugger connected to your process. Now this is important because once you start boofuzzer, hopefully we'll get a crash. And if we get a crash, well, we need to look at the debugger so we know what the heck's going on. All right, whenever you attach, you can see down here at the bottom, actually my picture, my video camera is stopping it, but down here at the bottom, whenever you either launch a process or attach to a process, it'll always be paused. So you have to click the play button or go to debug and run, and that will unpause the application and allow it to run. All right, so we are attached to the process. Now all we need to do is just fire off boofuzz, and we can start fuzzing this application and see if we can get it to crash. So here we go. It's just throwing all kinds of crap at it. And if you look over here, you can see that it's just sitting here churning away, and you can see that we're making a bunch of connections, and boofuzz is just going to keep doing its thing until it either exhausts all possibilities or we generate a crash. And as you can see here, it stopped. It's not getting any response back from the server. Let's see if we crashed. And sure enough, we caused a crash. Because if you look down here, it says access violation when executing 2F, 2E, 2F, 2E. And that's right here, as we see, as our instruction pointer. Let's see if I can make this a little bit bigger. Nope, that is not better at all. I really hate the fonts on this. That's going to have to do it. But anyways, we got a access violation, and our application has crashed. And we can see here in the buffer, we have our TRUN command, space, and then it's got all these, you know, / periods, more /, etc., etc. All right, so awesome. We made it crash. That's great. Not only did we make it crash, but we caused it to overwrite the EIP, which is the instruction pointer. And if we can control that, then we can control execution, and we could, you know, overwrite that with a memory address and cause it to execute code, and boom, we just hacked something. All right, so now what we want to do is figure out what exactly caused it to crash. So when boofuzz is done, where'd my thing go? There it go. There it is. So when boofuzz is done, it will create this folder, and inside there you'll see there is this Sqlite database. And inside that database, it shows all the different, test cases that it threw at the server. So let's go ahead and take a look at that. So I need to copy that. If I can type. Okay, so what I'm going to use is the Sqlite Db Browser. This is another free tool. You can download it from wherever. So let's go to Open Database. And then here we go. So up here, you can see table. I know it's kind of small, but right here it says table, and it shows the different tables. And then over here, you can view steps, and this is all the different test cases that it generated. So you can see in this instance, it created the command TRUN, it used a bunch of spaces and some A's, and that's it. So what did we have for our text? It was the / space period. So I'm going to scroll down this to make it a little bit easier. I'm going to filter this by just the send. So now we're looking at just all the commands that were actually sent to the server. Nope, none of those. So sometimes they can be hard to see because they get truncated if they're really long. Like right here, it just shows 3 dots, but actually it's something much larger. Aha, here it is. Okay, so what I was wanting to find out was how big was the buffer that it sent to the application, because we need to figure out, how large was that buffer? Because if the buffer was, let's say, 100 characters, well, that's important to us. We need to know that, because when it comes to writing our exploit, we need to know, how many characters, or rather how many bytes we need to input so we can overwrite that buffer and hopefully eventually overwrite the EIP. Hey, appreciate that subscribe, Kenny. Thank you very much. All right. So right here, it only shows 512 characters. So don't be misled by that. It actually sent more than 512 characters. It just truncates at 512. So to find out how big this buffer actually was, what we want to do is see what was this test case. I think 83. So let's go ahead and clear our type up here. And then let's find that test case. Actually, I think I need to do this a different way. So step. And then, yeah, where'd it go? It's 84. Oops, actually not step. Hold on. What was it? Send, not step. So send, I think it was 84. Nope, not 84, it's 83. So if you look right here at the end of the timestamp, there's a number, and this one is 541, and that's basically each event that's taking place. We want to keep an eye on that because we'll need that here in a second. So now I'm going to scroll to that 541. And is that it? Yeah, here we go. All right. So, and we can see right before that, it said it sent 10,005 bytes. So we know that the buffer is somewhere's under 10,005 bytes. Where it is exactly, we don't know, and that's what we need to find out now. But we know that it's going to be, at least 10,005 bytes to overwrite the buffer. All right. So actually, why don't I talk just a little bit about what exactly we're doing. So basically, you have a buffer, and this is going to be very simplified, and it's a little bit more detailed than this, but let's just say you have a buffer and it has 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bytes. And let's say you were going to use this buffer to store somebody's name. So in your application, whenever somebody types in their name, it gets stored in this buffer. But you only gave it 10 characters. Some people have names that are really long, and what happens when somebody enters a name that's longer than 10 characters? Well, it's going to overflow that buffer. And if they have no bound checking in their application, it's just going to keep writing to memory until it's just going to overwrite whatever's after this buffer. And in most cases, that's going to be your instruction pointer or the EIP register. So if somebody typed their name here, I can't think of a name that's that long, so I'm just going to type in some crap. And let's say they kept typing their name. Well, it would overwrite that EIP. And the EIP is what tells the computer where to go to next and execute code. And if we can control that EIP, we can tell the computer, hey, go over here to this buffer and start executing from there. Because that's where we're going to put our shell code, and the computer will say, okay, it's a valid memory address. I can execute what's there, so I'm going to execute it. So that's a very simplified, explanation of what a buffer overflow is. I'm going to make a detailed video that goes into a lot more detail about buffer overflows. All right, so now what we need to do is we need to determine exactly how big is our buffer. And there's a few different ways to do that, but I'm going to show you how to do that in Immunity Debugger. What's really cool about Immunity Debugger is it allows you to basically kind of use like Python add-ons, and one of those is called Mona. And it's a very awesome tool for, bug hunting and trying to find exploits, or rather vulnerabilities in applications. I'm a little unsure if I'm still streaming on YouTube. Hey, if you guys on YouTube can still hear me, let me know. All right, I'm just going to assume it's working. All right, so again, I know this text is really small, but Mona's got some really cool stuff. It can really save you a lot of time and simplify the process of taking advantage of vulnerabilities. Man, I got to see if I can make this font larger. That's a little bit better. All right, so like I said, what we want to do is we need to figure out how big is this buffer. And Mona has a tool. Let's see if I remember what it's called. I think it's offset, or no, pattern create first. It's called pattern create. Remember, our buffer was 10,005 bytes. And the purpose of this is it's going to basically generate a set of characters. You then copy those characters you overflow your application with that, and it'll overwrite that EIP address that we were talking about earlier. And then based on what that value is, you can use that to determine how big the buffer is. Now I know that probably doesn't make sense, but let's go ahead and do that now. All right, so we can see Mona has created a pattern for us. I'm gonna go ahead and open that, and it has exported to a folder on our hard drive. So I'm gonna open that here. And here we go. So as you can see, it's got this sequenced text. AA0, AA1, so on and so forth. And this is how it'll be able to determine exactly how big the buffer is that we're trying to attack. All right, so we're going to take that buffer, but here's the problem. How are we going to get that buffer into the application to cause it to crash so we can see what the EIP is? We can't do that with Mona. So what we need to do is go ahead and start writing our exploit script. That way we can, make a TCP connection to the vulnerable server and then send this buffer, which is going to cause it to crash. And then we can review that EIP to determine how big is our buffer. All right, so let's go ahead and get back to our code. Actually, we don't need a VS Code. We can just do this here. Oh, it says my stream status is poor. Well, that's sad. Oh well. Is what it is. All right, so let's go ahead, create a new Python file. This is going to be our exploit. And this, so the first thing we need to do is import the socket library because we need to be able to make remote connections to the server. So we're going to create a socket. We're going to specify AF inet, basically saying TCP, and we're going to create a socket stream. All right, once we have that, we can call the connect function. And again, we want to connect to the VULNSERVER, which is 192.168.254, 128, I believe, yes. And then port 9999. All right, so this will connect to the server. Once we're connected, we want to send our command and then send that big buffer of data. But before we do that, the server, when you connect, it sends basically a banner message. We want to grab that before we do anything. So we create a variable called data, and then we'll call the receive method, and we tell it a byte size of 1024 bytes. And then we'll go ahead and display that to... Actually, we don't want to display the banner message. We know what that says. But what we do want to do is send our buffer. So in Python 3, everything needs to be bytes. So if you preface a string with this B value, that's basically telling Python that treat everything in here as bytes. Okay, so we want to use our TRUN command and then space, and then we'll concatenate that with our super, super long buffer. All right. Let's see. All right, now that we, oh, actually that's not right. I need to close that off. Let's see. Okay, that looks right. All right, so once we do that, we again want to receive whatever the heck it might say to us. And this time we'll go ahead and display what the server sent back to us. And then finally we'll close the connection. I see one problem up here. I forgot to specify that as a byte. All right, I think that looks good. Yeah, go ahead and run it. If not, it'll let us know. Now, before we do that, we need to go ahead and restart our server because it crashed. So we go ahead and restart it. And then unpause it. All right, now we're ready to go. So let's run our code. Let's see, what did I do wrong? Oh, what did that say? Module socket has no attribute AFI. Oh, I know what I did. Forgot the E. Forgot a bytes again. All right. So as you can see, it says received TRUN complete. So our command executed. We sent 10,005 bytes, but what the hell? Our program did not crash. It's still running. So why did it not crash? Well, I actually screwed with this before, and I finally figured out that you need to have so if we look back at our command that caused it to crash, you could see we had this data in there. I found that we got to have that starting with that in order to get it to process. So let's go ahead and add that to our script. Let's try it now. All right, so we ran it this time, and I don't know, it's just hanging up there. It hasn't finished executing. So let's go ahead and take a look at our server and see what's going on. And we can see we have an access violation. So our program crashed. Awesome. And if we look here, we can see that I'm actually going to copy this so you can actually see it a little bit better. We have our EIP address, and that EIP address is 4338-6F43. All right, so what we're going to do is we're going to take that address that was in our EIP. It's not really an address. If it was a valid address, we wouldn't have got this access violation, but we're going to take that value and we're going to throw that into Mona to figure out how big the buffer is. So we're going to do Mona offset, oops, and then that value. And then we're going to hit enter. Mona's going to do its stuff, and then it's going to tell us how big that buffer was. Where to go? Actually, it looks like it did not. Hold on. Missing a parameter. What? I don't remember that. Missing mandatory argument. Let's see. Mona is not happy about something. Let's see. Oh, I used the wrong command. It's not offset, it's pattern offset. And right here, Mona told us that the buffer size is 2004 bytes. So now we know how big the buffer is, 2004. So let's go ahead and start working on our exploit script. So let's pull it back open. Okay, now we can make some changes here. We can go ahead and get rid of all this crap. We don't need it no more because we know how big the buffer is. We do need to add to the beginning there, and then we'll do A times 2004. And what that'll do is it will print 2004 characters of the letter A. I'm going to wrap this in the stir function. That way it'll just convert it to a string. Not really necessary, but all right, so cool. So now we're just going to test out this buffer here. So it should be 2004 bytes will be the buffer size. And then these next four characters should overwrite the EIP or the instruction pointer. So I'm going to put in there DCBA, and if that works, our EIP should decrement from basically the ASCII. So the ASCII equivalent of A is 42, so it should decrement from there. So let's go ahead and try this. So I'm going to save that. We need to restart our application. We'll go ahead and run. And now let's fire off our exploit. Oh yep, forgot bytes again. All right, let's try it again. All right, looks like the server crashed. It sure did. And here we go. 41, looks like we might be a little bit off because we have 42, 43, 44, and then 41 should be 45. So I think that might have to do with the / space period. So let's modify that and see if that is accurate, because we should be overwriting that EIP exactly. Let's try to get rid of that /. Let's go ahead and run that. Interesting. Well, we can see here what we got going on. We got / space. Oh no, actually, you know what, guys? We're right. We got it right that time. So it's 41, 42, 43, 44. So that's exactly what we're going for right there. So great, this is awesome. We are getting very close to being able to gain control and execute our own code or our own shell code. So this is perfect. So let's take a look here. So here's our buffer. And down here you can see all of those A's. And then the end of the buffer. So what we want to do is we want to overwrite that. But we need to get to the stack pointer. See the stack pointer? It's right here. It's this F9C8, which points to right here, which is the end of our buffer. So we need some way to get there. But here's the problem. We're not going to know what that memory address is because it's going to change every time the application runs. But we have to have that in order to get the our instruction pointer to our buffer to execute our shell code. So luckily there's a trick for that. And that's called, basically it's just a jump ESP. So we need to be able to call a assembly instruction of jump ESP. If we could find that, like a static memory address and a DLL or the application itself by chance, actually it's probably very unlikely, most likely in a DLL, if we can find a DLL that doesn't have any sort of protections on it and has got a static address to a jump ESP, well then we can point to that memory address. It will execute that jump ESP and then it will point to our buffer here and execute our code. Now there's actually a way to do that, and you can use Mona to try to look for these. This is why Mona is so great, because it can do all this heavy lifting for you and save you tons of time of trying to search through shit. So we're gonna do Mona, and then I think it's just jump. Yeah, so we want to jump. Actually, first what we want to do is we need to figure out what modules would be basically like DLLs that are running with this application. So we'll do Mona modules, and we'll load our modules. And we can see here that we have several loaded. We have this ESSFunc.dll. We have some Windows DLLs. Actually, I think all the rest of them are Windows DLLs. But on this ESSFunc, we can see that it has no exploit protections on this DLL, which is a good thing. It'll make our life easier. So awesome. We can go after this ESSFunc.dll and see if there's any jump to ESP instructions within that DLL. All right, so now we got that module. We can use it for our next command. This is going to be jump-resp. And then I think it's the DLL. I think I got that right. So let's go ahead and run that. Nope, that's not right. All right, boom. That's right. You don't have to specify a module. It'll actually automatically go through the modules that are already loaded with the application. So once it's done, I don't know why, it sends you back to the main screen. You just need to go back to the log window by clicking the L up here, or by going to Window Log Data. So boom. So we can see that it found several locations where inside this DLL there is a jump to ESP instruction, and this is the memory address right here. So if we overwrite our EIP with one of these memory addresses, it should call the jump instruction, which will send us to the stack pointer, which is where we need to go because that's where our shell code is going to be. And so if we don't get to that buffer, that specific location in the buffer, our shell code's not going to execute and this exploit won't work. So I'm just going to randomly choose one of these. You know, I've had instances where I'll try one, it doesn't work. So if one doesn't work, try a different one. All right, so I'm going to copy that address. So now we want to go back to our exploit code. Let's go ahead and kill that one because it crashed. So let's edit our file. I'm just going to go ahead and create a new variable called EIP. I'm just going to paste that address there. So our platform, our computer, Intel platform uses Little Endian. So there's Big Endian and Little Endian, and that's the order in which you write these bytes. It's very important that you do it in the right order. And since we're using a Little Endian, we're going to put them in there backwards. So we're going to do EB 11 50 62. So that is the memory address of our jump ESP. All right, so what we're going to do now is we're going to replace that. We're going to put that in right here. So we're going to, basically what we're looking at now is we have our command. We add our / space period. We put in 2004 letter A's because that's the buffer size. And then anything after this point is overriding the buffer. And what it's going to override is the instruction pointer. So, or excuse me, yes, the instruction pointer. So we want that to point to our jump to ESP, and that's going to send us to our buffer. So let's go ahead and put in where our buffer will be. I'm going to put in more A's here. And let's say we'll do, I don't know, times 500. All right. So let's go ahead and save this. And we're going to see if we successfully overwritten the EIP with the memory address of the jump to ESP. So we saved that. Let's go back and restart our server. Okay, server's running. Let's fire off our exploit. Oh, as always, forgot to specify bytes. All right, server crashed. That's a good sign. And what happened? So we have an access violation. And why is this? What's going on here? I can't see all of my registers. Oh, I changed the font. That's right. I screwed things up. Oh, or did I? I don't understand why it's not showing the EIP. Give me a second. Let me try to fix this so I understand what we're looking at. Ah, there we go. I didn't know you could drag it like that. Okay, so here we go. Our EIP is 00F7FFC3. What the hell? That's not the EIP we entered in, right? Let's go back to our code and take a look at that. No. We wanted the address 625011EB. So how the hell did we end up with this other freaking memory address? Let's take a look at that real quick. So if we look at that, F7FFC3, well, that just so happens to be our buffer right after our excuse me, it happens to be, actually let me change something so this will be a little bit more obvious. So let's go back here. Let me just change this to B. Oh, that's not right. Restart the server again. All right, play. Now let's go back to our exploit. Let's run our exploit. Crashed. Okay, so this time we can see that here's all those A's that we entered in, and then here's all those B's that came after our EIP. I should have said a breaker. A breakpoint would have been a little bit easier to understand. But basically what happened is our jump to ESP worked. The stack pointer is pointing to the buffer where it starts with the B's, and that's this memory address right here. Now we just reran the application, so it's changed. It is F3F9C8, and we see that right down here where we have all of our B's. So if this was actual shellcode and not just a bunch of B's, well, it probably would have executed that code, and at that point we would have code execution. So that means we hacked this program. We can then send this very specially crafted buffer of data to the application, cause it to crash, overwrite the EIP with the jump to ESP, point it to our buffer, and execute our shellcode. So now it's time to actually try that. So we need some shellcode. You can get shellcode from all over the place. There's tons of websites out there that will create shellcode. You can use Metasploit to create shellcode. It's easy to do. I already have some shellcode that I'm going to use. Now it's very important that you get, if you get some shellcode, make sure it was developed on your specific platform. Like if you're using Windows 10, 21H1 or whatever, you might want some shellcode that was, generated for on that platform or for that platform, whether it be 32-bit or 64-bit, because there can be differences and nuances between them, and it might not work. So the first set of shellcode I'm going to try is basically just the calculator. I'm just going to try to execute the calculator. I like starting with just some simple shellcode like that. Nothing that's like socket based that's going to make a reverse shell or anything like that, because it's just a little bit easier. You're gonna have less chances of things not working. So that's why I always like to use calc first, just to make sure my exploit's working, it's doing what it's supposed to. And once I got that down, then I'll change my shellcode to something a little bit different. Maybe a reverse shell or something like that. See if that works. If not, debug and see what the heck's going on. But generally, once I have things working with the calc shellcode, I can throw in any other shellcode and I'll be good to go. So let's go ahead and open our script here. So I'm going to create a new variable. I'm going to call this one calc, and then I'm going to paste in my shellcode. All right, so that's our shellcode right there. And basically all the string of hex bytes is basically assembly instructions that will execute the Windows calculator. All right, nice. So we got our shellcode ready. let's go ahead and insert that into our payload. So I'm going to add it right here, right after the EIP, because we want to overwrite that EIP, which will then call the jump to ESP, which will put it back to the stack pointer, which will be sitting right here at our shellcode, and hopefully everything runs. All right, so let's go ahead and save this. Let's go back and restart our server. I don't know if our server's running. Nope. Let's restart it. All right. All right, now let's fire off our script. Now, if everything works, the Windows calculator should pop up on our screen. So let's see. All right, it definitely did something. It crashed or something. So do we have calculator? We do. Boom. We got code execution. So if we look down here, no, actually it's already went on beyond that, so we can't actually see that memory address, but you can see the code down here where it's executing the calc process in Windows, and it opened up our calculator. So awesome, we got code execution, we are hacking this shit. So now what we want to do is we want to get something more useful, like a reverse shell. So, you know, I can actually get a command prompt on this server, and because once I have that command prompt, then I can start executing commands. I can put, you know, my back doors on there or whatever I want to do. You know, that's always going to be kind of the next step. Once you get that code execution, is generally you want to start a reverse shell or something along those lines. Maybe bind, you know, a command prompt to a port. But the bottom line is you want to be able to execute commands on that system. All right, so let's close this off. And generally when there is a service running on a Windows computer, it generally runs as the administrator. So what I want to do is I want to go ahead and relaunch the VULNSERVER, but I'm going to launch it with administrator privileges. So I'm just going to go ahead and tell it run as administrator. All right, so now it has administrator privileges. So now what we need to do is we need some reverse shellcode. I happen to have some here. And let's go ahead and edit our exploit. All right, so let's open this up. We can leave that there. And I'm going to paste in my reverse shellcode. I think it's running on port 4444. I don't remember. We'll figure it out. All right, so there's our shellcode. So really, we should be good. We've already figured out this buffer. We have our specially crafted payload. All we need to do is just tell it replace that calc with shell, and it should run our reverse shell. So I'm going to save that. Did I restart the server? It's running. So let's go ahead and run our exploit, and if all goes well, we should launch a bind, basically a Windows command prompt to the port 4444. We can then use Netcat to connect to that, and if all goes well, we should have an administrator command prompt. So let's run the exploit. We ran it, it paused, that's a good sign. Let's go back and look at the server. It hasn't crashed, it doesn't seem. Let me open up the debugger. Actually, I don't even have the debugger open. We don't need the debugger open, but the application is still running. Everything looks good. Let's go ahead and see if we can, let me go here. All right, now let's run Netcat, and this should be running on port 4444. Cross our fingers, here we go. Boom. Now, I don't understand why it didn't give us administrator privileges. I can't remember if Bob is an administrator, but the point here is that we were able to bind a command prompt port 4444 and gain remote access to the server by just sending that specially crafted buffer of strings. So I'm kind of curious if Bob is an administrator. I forget, who am I? I think it's all. I guess he's not. Oh yeah, he is. He is. That's why. Okay, yeah. So Bob is an administrator. So we got an administrator prompt. I mean, look at all these permissions. So we're good, guys. Man, we hacked this. So that's basically the very simple version of a buffer overflow. They can get more complicated because Windows has exploit protection, and in future videos we'll go through and we'll turn some of those on, because right now I have all those turned off because that's kind of like the easiest, simplest scenario. And then what I'm gonna do is I'm gonna start turning those on one by one, and we'll look through how that causes basically memory addresses to change. What do some of those exploit protections do, and how can you basically overcome them? Because with most of them, there are methods that you can use to basically circumvent them and still get around them and, you know, execute buffer overflows. But they can get pretty challenging and difficult quickly. But all right, guys, this was fun. I'm going to be working on a more detailed video that walks you through this process. I'm also going to be doing some videos that kind of gives you basically the beginner's guide to assembly, because when you start doing this, you do need to know some basic assembly. You do not need to know like everything there is to know about assembly, but you do need to know some basics, how it works. What are some of these different instructions? What do they do? How does the stack work? What are all these various registers for? Because once you understand that, you get a better view of how the computer is moving through the memory and executing code. But again, you don't need to know all this, but I'm gonna create some videos that kind of go through the basics that you need to learn to start doing some of these, you know, what I think are very fun exploits. You know, it's always cool when somebody finds a bug in some software and writes a vulnerability, but it is super awesome when you find a bug in some software and write that vulnerability. And I want to help you guys learn that. So if you haven't subscribed to my channel, I'm going to be doing more videos. And guys, I will see you on the other side.